before I became an academic. So my approach is actually very different from most of the traditional academia. Okay. So first of all, I want to show you. Actually, let me see this. We'll use this guy. This one here. Another pointer. Okay. This is UT Austin. UT Austin is big and actually in football. 2004, we won the national champion. That's why we like the line number one. 2005. Okay, so this is the president's office somewhere around here. So when I start working with the higher up, said that anytime you make a presentation, you need to use this. So I just listened to the deans and probably the dean and the vice president that we should use this. This is what I mean. Number one, 2005, and I'll make one more comment, and I'm going to start probably my first lecture. Our coach makes $5 million a year. Since we are state, he is the most highest paid in the state of Texas. Okay, so calculate that his salary is 30 base professor. And what I said is it really worth times more than? Don't know, but that's what we have to pay the highest actually post to UT, and right now a little bit more than. Okay, so that's my job. So I'm going to tell you about what I'm going to actually still have a little. I'm writing a commission by Cambridge Press. It will be 2019. These are different that I am writing according to chapters. So this is actually a short version of what I'm going to actually lecture. I'll tell you a little about what how you actually test them, what kind of you make and put in later in order to get temperature, rate. I think enough we start to get the property. We have to first go characterize, and you have to do modeling. And I explained to you why it is so important. If you are just a materials guy, you will come up with materials and you probably do some characterization, do some testing, but you never actually do much modeling. So what happened is you develop material. If somebody asks you about how thick it's going to be, a certain actually condition, you cannot predict that. So that's why you have to go to modeling. All these modeling, all these computer codes are actually funded by our government. Okay, so if you don't actually do all these kind of things, this is what I'm actually lecturing today, is the methodology that we are trying to solve the problem from the beginning, actually all the way to the end. So that's most important. It was 4 years ago, I went to NASA Johnson Space Center and asked my student to give a little bit of presentation what they are working on. And they actually learned that I was the only academia actually is doing all these things. Why? Because most people will just do touch part of it. But I'm trying to solve the whole actually problem. And that's why they liked the approach, and they said NASA, Johnson, and other center are doing all these at the same time. So I'm going to actually give you a brief introduction. This is the book I'm going to write. And I find out ablation is very actually specialized. The last book that was published on ablation is called Ablative Model by a French actually a researcher. But he only talks about modeling. But before then, almost 20 years, nobody actually talked about ablative. Ablative is very, ablation is very actually restricted. But without that, you cannot actually do all the sizing of material to do. I'll give you some example for thermal protection system. as well as for rocket motor. So I'll give you some example what we have been working on. Okay, so this is pretty much the outline of my seminar. I will give you some example about nanostructure. Nanostructure is kind of my expertise. The materials that we have been developing are what we call nanostructure. Okay, and I'll explain a little bit more about it, and then I'll give you some definition of what do you mean by char yield, thermal stability, and you actually calculate all these kinetics. We use a system called Oxy-acetylene test bed, and with advanced diagnostics that we will see how the material behaves during testing. And the next one I'm going to show you is ICP, is Inductively Coupled Plasma. That is a new device that was funded by NASA Johnson that is now installed at UT, and I have access to it. It's actually from the Aerospace Engineering Department. Another area I'm going to talk about is in situ ablation recession sensor. Because you make a material, if you actually do not do all these sensoring and capture data, you don't know what's happening to the material. You only know at the end. So that was actually developed by my research group. And every one of those actually is funded by Air Force or NASA or Army. And I show you the list. And another area I'm going to talk about is char strength sensors. Because if you have a material, char strength is very important. And that idea actually came from the Air Force. So we developed a char strength sensor. And after all these actual experimental, we need to learn about the thermophysical properties. You have to really actually characterize the property before you actually go into ablation model. Okay, so that is kind of the sequence that we solve a problem. We develop material, we have sensor, we test it, and we characterize them, and we will do modeling. Okay, I want to share a secret with you. My background is in combustion, actually. All my work, graduate work, is in combustion. And I started doing ablative when I was working in industry. So that's why I'm not afraid of actually sensing, testing, and also modeling. If I'm a truly materials guy, I may not understand some of these. So all my mechanical engineering and all my application is aerospace. I'm not even an ASME member because all my work has been presented in AIAA. So anyway, so I'm going to tell you a little bit more about that and give you examples. Okay, so look at this. This is the whole list that I actually divided into ablation research, flame retardant polymer research, conductive polymer research, as well as other areas to work on. All these little bullets that has been probably 20 years that I've been working in academia. The things that I did actually in industry, I didn't list them, okay? But these are, every one of those are actually research grant or contracts that we touch over these, and that's why we group all these. Instead of going through actually all these lists, I'm going to pick certain examples to show you how we are doing ablation research. And I think one area that Monday I talk about is additive manufacturing. That's another area that we work on, develop material. Okay, so this is actually, I'm going to give you two examples. This is all nanostructure ablative. I'm going to ask a few questions. Anybody actually do nanostructure materials? Can I see a hand? Huh? No? Kathy and probably Professor Bateman. But not everybody knows about that. Okay. But when you actually look at the literature, that is the next generation of ablative that all over the world is looking at. Why? Because ablative has been around for a long time. But for a while, this whole area is dormant. And nobody actually do any more research in that area until nanocomposite came in, and you see a lot of publication that deal with nanostructure ablative. Okay, so that is state of art. A lot of people are doing that, and we are doing that. And we actually, these two research grant or contract actually came from Air Force. A lot of my research has been funded by AFOSR. Probably Pierre knows about it, and AFRL. They actually sponsor a lot of my research for the past probably 15 years. Okay, I'm going to give you some example. Okay, so we were developing a new class of nanocomposite for rockets. Okay, so we were developing these materials for rocket nozzle, and they fund my company did that, AFOSR. So the whole idea is, can we change the phenolic resin with very low loading of these nanostructured materials and use rayon carbon fibers and make a new material. Okay, so that's the reason behind it. And since I work in industry all these years, so I work with SciTech engineer materials that we have the formulation and send it to SciTech, and they will make scale up. Okay, SciTech is now by SciTech Solvay. Okay, so what we do is we do everything in the lab. When we work with other companies that are doing this business and scale up, okay, that's the approach that I'm taking. I will buy all the materials off the shelf and formulate in something nobody have done before. And if I do everything in the lab, that who's going to take over? The companies. SciTech, Solvay is the biggest company in making ablation. We have a very good relationship with them. Right now, this is one of the projects. This is probably like 12 years ago. And we did that, and we tested with another instrument called SSRM, and we simulate the AL203 coming from the propellant. You see this particle impingement. Okay, so eventually, these were actually funded by AFOSR, and we published it. As soon as you, oh, excuse me, what is this going on? What should I do? Can somebody get rid of the screen? Thank you. Oh, it's gone. Hopefully it won't pop up again. Okay, I think Professor Bateman asked me when it started getting to ITAR. As soon as you send all this material to Air Force, it's ITAR. I cannot talk about it. But anything that we develop is called basic science. It's funded by FOSR. All the things I'm going to talk about is actually done in my lab, and we can publish it. It is published in Journal of Spacecraft and Rockets. We publish that. As soon as you hand the material to Air Force, testing it using the rocket motor is ITAR. Okay, so AFOSR is actually funded basic research. So that's how I get around it, because I have students, if they're working for a PhD dissertation, and he said, ITAR, well, what are you going to do? You cannot publish it. So the same thing, right now we have a NASA project. All the material that NASA gave us as ITAR, he cannot put it in his dissertation. But all the other narrow material, he could talk about it. That's how we get by, okay? So the important thing is we actually have what we call formulate resin, reinforcement, and filler. So these are the different formulations that we come up with using a phenolic. Phenolic is the traditional material. We actually, this is actually a material made by SciTech. We always use a control, and then we change the filler using like clay, using PARs, also using carbon nanofibers. Those are the things that we are working on. Okay, so this is all done. This is actually all done at SciTech. We give them the formulation, and they will make it. So we don't have what we call scaling problem. If SciTech could scale it up, they could make us a product. So that's kind of different between my research and a lot of my colleagues. I always find an industrial partner to make our formulation. Okay, I want to concentrate a little bit on this, what we call technical results. So you can see that I flow plots here. Density is the most important thing in all the material that we develop, because you have to put in rockets, you have to put in certain things. If you have a very high density material, you're not going to fly, period. Okay, so I have a what you call a control. This is called trade name MX4926. It's a carbon phenolic material made by Cytec, and we add PAS in there, we add clay in there, we add carbon nanofibers, and you take a look when you draw across the density. All these different formulations we did have a lower density, so that is checked. That means that if your performance is better than the control, you have a better material. You have a material high density. Then I had to do a lot of song and dance and say, oh, this is really good, but the density is higher. We could calculate. No, that is actually not very good way to make material. If you could make it a less density, then you could basically say the performance better. Then you have what you call wave saving. The same thing for NASA. Okay, so we did that, and we also measure what I call the ablation rate. Okay, I think this thing is going up. Couldn't see that. Okay, let me try this. Anyway, this is ablation rate right here. Okay, and you can see that when you draw a line across for ablation rate, not all the formulation will work well. So that's also another parameter we need to look at. So another thing I want to show you is the surface temperature. We actually have IR, two-color parameter, to check the surface temperature during the testing. So certain ones are higher, certain ones are lower. As a matter of fact, that and you look at this, only the carbon nanofibers materials have a higher surface temperature. Next thing I want to show you is the backside temperature. This is also a very important parameter you need to fulfill, because all these ablative, you're going to bond it onto mostly a steel substrate. If you actually have a temperature is beyond the high temperature adhesive, you're going to debond. It's no good. So those are the things actually we look at, what I call the parameters that we should check for all the materials. One thing I want to point out to you is all the nanostructured material have a lower back temperature. These are actually what I call heat soak temperature. What it means is your experiment is going to finish and the thermal wave is still passing through the ablative material, and we measure what is the highest temperature. So all the material that we develop actually have a lower backside, which is good, because otherwise, I give you an example, ceramic. Ceramic is really good, but ceramic passes through so fast, it's going to have debond. Ceramic is good. It doesn't ablate, but ceramic is not a very good ablator. Okay, so those are the things that we need to work for design constraint. I actually used to design rocket, so I know all about it. And the thing is, when I talk to now Northrop Grumman, it used to be Placom, that I used to be trained by them. So whatever they do, I understand. They will not say that this professor doesn't know anything. His knowledge is just not very practical. Well, I used to work for them. And I still actually have very good relationship with these companies. And that's make my research a little bit different from most of the academics. Okay, so that's what we call look at the silicon, and we were able to present that and give it to AFOSR, AFRL, and that become ITAR. I cannot show you any of those results. And eventually, they're using rocket to test it. Okay, so that's how I cut off from AFOSR to ITAR data. Okay, so that's one example. Another one, we publish a lot. That's why all these you could actually find out on these citations. This one is also jointly funded by AFOSR as well as AFRL in Edwards, California. So this one had to do, the first one to do with not rocket nozzle, the second one to do with insulation. Okay, so we start actually using material. These material came from Bayer, the thermoplastic elastomer, and then we use the clay came from industry. We also use multi-wall carbon nanotube, came from Acma, French company. And we use carbon nanofibers, came from Applied Sciences. So that's what we did. And we compounded, go back. And we actually compounded using twin screw extrusion. And we have all these different loading because we do not know which one is better. So we actually have to do a loading study from 2.5 all the way to 10, and with these different nanomaterials. After we compound all these, we will test using a very high heat flux. And we have our own, this is the first generation of oxy-acetylene torch that we used, and actually we were placing thermocouple at different ends to get the temperature gradient during the test. Okay, so I'm trying to show you some data, but I'm not actually going to explain the data more. But I'm trying to show you the methodology, how we solve a problem. We collect all these data and we start looking at, this is recession. Of course, actually the lower the better. Okay, so we know that the loading, and we plot everything, and we find out which is the one that will give us the best ablation resistance. That's one things that we look at. Next thing, we look at peak, what I call peak soak temperature. So this is picture for clay, and then these are the different like thermocouple we put in at different distance, and we will be able to get all the data, and we look at when is it actually going to peak. Okay. After we get all these data, I always ask my students to do, you need to do SEM, scanning electron microscopy. That's what you learn about the mechanism. So I'm showing you this. It's a clay. So you actually, this is what I call char surface. The heat is coming down here. Clay is a one-dimensional nanostructure. So what is you're seeing is all these are stacks of clay. There's the mechanism that make ablative works well using clay. Okay, so we learn it from SEM for post-test material. So this is what you saw for char structure for clay. The difference is they actually have all these clay that it will stop. Clay is a ceramic, and it will work really well for ablative. Next one I want to share with you is multi-wall carbon nanotube. Multi-wall carbon nanotube is very different in terms of structure, of like different from clay. You see this very small multi-wall carbon nanotube is roughly 20 nanometers in diameter. So you form what we call a carbon network. The other one actually form a ceramic shield. Very different mechanism. And that's how it really worked for ablative that we developed. And as you can see that this one is actually 10 micron. This one is even actually higher magnification. So next one I want to show is, what? Can somebody help me? It will go away. It just come up, right? So you see underneath, okay. All right, it just, okay. So underneath here, this is carbon nanofibers. Carbon nanofibers is 150 nanometers in diameter. You can see there's also the mechanism carbon network, but they're bigger. They're 10 times bigger. So that's why we look at what we call examine the structure and learn about the mechanism. So that's what I tell my students to do. Once you learn about the mechanism, you could actually solve another problem. Okay? Well, this is actually very new. This is actually just been published. This is some work that, and I need to brag a little about it. This kid is an undergrad. He just graduated under me. He was able to write a journal paper, and it's been accepted. That's how I work with my students. Of course, graduate students are important, but some undergrad are phenomenal. I work with him, and he got a paper published. Just came out last month. Journal of Spacecraft Rockets. So he did that. Okay. We were looking at experimental characterization of a new material called using the resin is polysiloxane, and using silica. I better go this way too. Okay. So that's what we did. And this has been published. Okay. And what I'm showing you, the methodology, how we start from the lab all the way to testing. Okay. So why are we doing that? Because it's for TPS. Okay. And this resin was developed by a company. They came to me and say, I would like you to make this material into thermal protection system, TPS. So we did all that. So that paper, everything that became marketing tool for them. They pay for that. They have the intellectual property. It's not like, oh, I hold all these. No, pay for that to use it. So this is actually a very, very interesting system. And I'll show you a little bit more later on with the yield. So we were able to develop using their resin is a pre-ceramic. Okay. We were able to use it and make fiber reinforced composite using silica. And we were able to evaluate fiber versus resin ratio and better understand how it works. Okay. So this is what we did. And we compare with silica phenolic, which is a material, has been around for a long time, is also made by Cycad. So we always what you call a control. Because if you mix something up, how you know it's good? It's not say, Dr. Koo said it's good. No, you need to compare everything in industry. And this particular material has been around for a long time, 40 years. So we compare with that, and we were able to compare and make it in our lab as well as get the material from Cytec. So we're able to do that. These are the structure of the silicon polysiloxane, and this company provided that is very high char yield. Okay, and we'll use the same methodology that I talked about earlier. TGA, look at the char yield, look at the MCC, and we'll look at heat release rate. We'll actually measure the density, and the difference is we will also for ablative oxy-acetylene torch to find out ablative properties as well as performance. So all these, and Kathy, this is a definition. It came from NASA. When you look at the literature, people say char yield. Well, they use a different definition. I cannot compare. But this is the definition actually came from NASA Pika report. You cannot get a copy. This is ITAR. Okay. But the definition, I choose it, and this is what you do. You have the size, you did it, and that is the definition of char yield. And we compare every one of those that we got from the industry. Okay. So then I know. Take a look at this char yield. Take a look. That this is char yield coming from phenolic, which is lower than this particular resin. Using the same definition, it's 86%, substantially better. Char yield is only one thing that we look at. But if you have a high char yield, you're going to actually maintain your ablative performance. So that's what we start looking at. So we show that, actually we showed to NASA. NASA now is using this material for another application. Okay, so besides the TGA, we also look at the DTGA, which will tell you how many reactions there is. Actually, like phenolic, a different reaction, but actually the polysiloxane only have one peak. Okay, so those are the things that we start learning about. Why is it so important? So we do a fair amount of analysis, and we look at flammability. This is for ablation, but it's not for. But can I actually the tools that we have and see whether we could have a guess of the performance? So what it's showing us, this material actually have a lower heat release rate, which is good for not for ablation, but for flammability. So that's another good thing. Okay. Now we plot that. Okay, and basically one is lower than the other. You're comparing it to control. Okay, then we start actually vary the resin, the fiber, and the filler for this particular free system that we made. There's no filler. Okay, this actually F0 is similar to what you actually compare with the Cytec, except Cytec material, except that you don't have a silica filler. So these are the ones that we are doing in the lab. Okay, and the density. Well, it's showing that all of these have lower density than the control MX2600. So if we have a low density, you have a better performance, you have weight saving. Okay, so we do TGA. First, I did it for the resin. Now we're actually doing for composite. Take a look at the composite. It is very, very high, 97%. That's extremely high. Okay, so this is what we do for using oxy-acetylene approach. We have we calculate the fuel ratio as well as we measure the heat flux using a Garden gauge, and we expose using 1,000 watt per cm square and exposure time. We have a carbon shield actually blocking flame wrapping around. Okay, so this is what we did, and this is all presented. These are my my K-team capstone team who designed all these, and I, as every capstone project, present a paper, and this is actually done in 2015, and it was presented as the AIAA paper. Okay, we have these instruments that came from NASA, the IR camera, high definition camera, and the other one is two color IR parameter. We will examine the surface of each one. Okay, and this is how it looks like before and after. All right, and we also measure the backside temperature and see when is it going to be, and all the ones we made lower backside temperature, less nation, lower side temperature. That's two checks. Lower density checks. Okay, and then measure the surface temperature, which is similar to what we did for the NASA project. We have two color actually parameter. Then emissivity is not an issue. Okay, they cancel each other out, and this is what you see, very high temperature, 2,000 degrees C during the test. Okay, and this is recession rate. Lower the better. Basically, you can see that this is actually the best active formulation we have compared with the industry standard. Heat soak temperature, they are all lower than the industry standard. We also measure the mass loss, all these. That's what we call develop a methodology. If every student follow this methodology, they use a different material, they get an answer. That's why we have numerous publications, because we develop methodology. This student use this student use this, but they're using a different. We have all the capability in our lab doing ablation as well as flammability work. Mass loss, okay, and oh, this is a video. Can you do that? Somebody help me. See whether you could do this video. This video is very interesting. It's an IR video, and you could see the material versus the one that we use. You could click both of them almost at the same time. Oh, sorry. Yeah. So you're seeing this is the one that is for IR, the surface. Okay. So the different color will tell you how hot it is. In the middle is the hottest. Okay. So now it's showing actually in parallel. Okay. Then this is the one for like MX is the industry standard. The other one is the actually the one that we made. This is Formula 2. Okay. Is it done? Oh, it's still going. You see, it's a 40-second. Okay, we capture all that. So now it's gone. Okay, so that's what we do, what I call advanced diagnostics. We capture all the things and we start analyzing that. And in the paper, can I show the video? I told them that just cut out all the frame. You compare, and this is what we're doing. Different, like 3 different material, and also the time. So you can see the comparison of steel frames. Okay, so that's what we have been doing. And can you help me with this high definition video? A high definition, you actually have a high definition camera. You could see all the material. It's not temperature. It's just how it works. Okay. So now you can see on the right hand side, that is the material that we developed. This is formula F2. The other one is silica phenolic. Then you can see the difference while you are testing that. Okay. And you can see the like it's forming some type of like ceramic around the F2, but on the other side, you don't see that. Okay, so because of this ceramic shield that we are developing using the polysilicon, it will actually make it more ablation resistant and also better. So those are the things that the two actually like device. It came from NASA. They basically gave us on loan forever. The good thing about it is, if anything breaks down, I send it back to NASA. Well, this thing doesn't work. Why do you fix it and send it back to me? It's even better that you have your own instrument. So they were giving us both the high definition as well as the IR. Okay, so that's what we do. All these measurement, and then we got steel flames. You want to know more about it, actually, the paper will describe all these things, okay? And we actually did a fair amount of SCM looking at the comparing like the material. You can see from here, the left-hand side, you see a lot of fiber. There's a silicon fibers. On the right-hand side, that is like the polysilicon. The frame is coming from top. Okay, actually in the paper, you have a little bit more discussion. And we find out that thermal wave passed through the polysilicon did not melt or actually polarize. So that makes it a better plating. Okay, so these are the ones that we did for looking at char shown area A, B, C, decomposition area, pyrolysis area, and virgin area. This is what we did for the material. Very, very detailed analysis. And mind you, this guy is only an undergrad. He just graduated while he's working. Okay. So in conclusion, we did all these things, and that was actually a very good material. This material, and I'm using for a new Navy contract. I have a new Navy contract. This is one of the material that we're going to use. Okay. So I'm going to talk about char yield a little more. These are different materials that we have. Okay, and that's what I call the char yield. All these material came from the industry, came to my lab, and use the same definition. And take a look at the char yield of the ones that we did, very high. These are what I call state-of-the-art resin system. These are commercial, not somebody from the lab. I do not take somebody's developmental. These are all I could buy. If I had the money, I could buy a truckload of these. Some of them are very expensive still, but I could buy them, okay? So we did all these, calculate the composition temperature, look at the char yield, and you will compare which resin is better, okay? The one that came up on top is the polysilicon, okay? So that we did all that before we do all these, and then we also do kinetic calculation. We do actually TGA at different heating rate, and always nitrogen. I don't want to do it in the air because nitrogen, you decouple air because of the oxidation. Okay, you did all these, and then we fit it into another computer code that we got. It's called isoconversion. which is actually used quite a bit in the academic. Okay, and we come up with all these, and we plot all these, and it's all every one of those actually did for my lab, my students. We calculate all these, and then basically we do experimental. Now we're doing a little bit more theoretical to understand. Okay, I think this is interesting because Jonathan is also actually an undergrad. So I'm going to show you some of the things he's doing. The two material, it's actually supplied by NASA, PICA, and AFCO. We have this thing, and we measure, use different colorimetry. The one that we depend a lot is it's a garden gauge. Okay, we plot it and actually look at the heat flux versus distance. And from there, we will use that particular distance and test the material. So we could go up to very high heat flux, actually low heat flux. We measure all these. And this one, can you show the video, please? This is actually quite interesting. It was all done by undergrads. So one side is the high temperature definition. The other one is IR. You could compare it, all the frame. So what you want to look at is we put in situ sensors there. You could see those thermocouples sticking up. That is what I call the time you need to burn the thermocouple. The thermocouple, and I'll explain a little bit later, is actually at different depth. That we calculate the instantaneous, actual recession. Okay, so those are the we develop. Recording. Okay, so we did all these, and actually, this is what we call in situ sensor. I'll give you actually there's another little section on that we designed this. It was funded by AFOSR. Is also basic research. We develop all these and use it into actually our research. So what I'm doing is got funding from different agencies. They pay me for this, pay me for that, but I put everything together to analyze ablative. Okay, so we did all that, and the same thing. We actually use IR to calculate all these. There's a water platforms where we could look at. They came from the NASA actually IR parameter. So this one is very interesting. This one is called IC. It's funded by NASA Johnson. Is actually now at UT. Basically, most people will use ICP to do re-entry vehicles. So Johnson fund us to my colleague in aerospace department and actually build this whole system. Okay, and this is a ICP. It's currently at UT Austin, and we are now using that to test the NASA project. Okay, so these are the instrument. Everything starts from ground zero. That we were able to do all that. I'll give you a video. Video. Okay. Oh, go back. How can I get the video? Please. Okay. This is the flame now. Self-explanatory. This is actually a PhD dissertation. So here's a flame. We're heating the air using electrode, and you will see all these instrumentation, and then later on you have a swing arm and swing your sample in there. Okay, I borrowed this actually Benton. He's defending his thesis this Friday, and I said you pass. Don't want to call in at 10 in the morning to sit in this station. Okay, so this is the flame, and you'll see a swing arm coming in right here, the sample. Okay. Something is missing. I think the video is something is missing. Is it come out? It's can you play back? Because you're supposed to swing arm, swing in, okay? And you see actually the sample in the flame and then swing out, and you will see a lot more things. Okay. Somehow, because the swing arm was designed actually by NASA. So you make sure the flame is steady state, and then you swing in the arm, you will be able to capture using actually this using the optics in there. Somehow it's something missing, but you don't find it.
Doing the same thing.
Yeah, it's not. It's supposed to have
Is there another video?
arm thing in there, but if you don't see it, that's fine. Okay, but this is what we do. We have a swing arm and swing it, and then you could capture for 40. I think he was using 40 seconds. Okay, so that was done, and this is what he described as a transfer table. They will be able to move that. Okay. And this is how you have an insertion mechanism that was developed by Johnson, and we were able to do all these. That's actually part of the PhD dissertation that's funded by NASA. Okay. The next one I'm going to show it to you in situ sensor. Okay. These are all published. The whole idea of is you actually have what you call a blade wire. This is the simple solution. You drill holes from the back, and actually you could space it where you want, but the sensor is 0.25. I bought it from Omega Engineering. Anything that I do, buy it. I don't want to go to somebody and say, can you develop something for me? And I cannot mass produce. Okay, so this is all made actually by us that will drill holes and use NASA material and make it. And these are the thermocouple readings from T1 to T4. T1 is the closest to the surface. T2, T3, and T4 are different distances. So we are able to measure all of these and actually calculate. This is AFCO and this is Pica, and we will be able to calculate all of these and plot it and have an in situ ablation rate. Okay, so those are the things that we have been doing, and we also measure the IR surface, and these are all actually in the journal paper that we just published, and comparing all these with different material. It's not just one material we have done. We have done numerous material, and it's all coming from the density. See, the top one is 0.3. We could go all the way to 1.83. So we could test all these material using this technology, and it's very reliable. Okay, so that's what we did. And the next one is ablation sensor, char sensor. This was actually all developed as a K project. Okay, and we measure all these homemade. And important thing is we were able to develop pathology. Oh, let's come back. It will go away. That measure, compare Kevlar. This is for in situ, like insulation material, and we have 7.5 multi-wall carbon and 11 and 10. So the error bar is very large, but we're able to look at that and say which one is a better in terms of actually strength. Okay? We did all these, and we calculated all that actually document in journal papers. So okay, so this is second last. After we did all these, important thing is, well, we need to know the thermophysical properties. Okay, well, this is a whole list that you need to characterize in the char state, virgin state, before you could do simulation, and that is expensive. Okay, so what we did is we actually have all these. This is also came from a NASA report. That's what they do for Pika. Pika is a material has been used for NASA a lot. They have all these characterizations. The other side, we cannot do anything on UT because we don't have the capability. So if you do all these things, you go into modeling. All these CMA, fiat, char, all these computer code, these are ITAR computer code. It was given to us by all three of them. Actually came from NASA. The first one, and if you do modeling, it has been around for a long time. The newest one is char. You could do 3D modeling. So that's what we do with all these, using the data that we collected at UT, and we start doing some hypersonic profile measure, actually simulation. But we start with 1D, and we use CMA and fiat because CMA and fiat are 1D. Those were developed a long time ago. CMA was developed at least 40 years ago. Fiat is a bit newer. We get all these, and we actually use the data that we collected for the material that has been characterized. The four material has been characterized fully by NASA as Pika, AFCO, carbon phenolic, and I think there's another one, I forgot which one. But those are the ones that the other one is silica. So those are the ones that we form a model and look at that. My goal is, can we form a model, what I call material response model? And now we're starting to build new material. Can we actually use this model to give us some prediction? Okay, that's what I want to see. Okay. No one is actually doing that yet. Okay, we're looking at using two versions, actually CMA 92, okay, and validate all these, and it's not very good. You can see that we're doing prediction. This side is prediction. This is all measured. We're no way close to what we expect. I think they're different. One is not actually a 1D. Second thing, we don't actually know the heat transfer coefficient of the oxy-acetylene torch. Those are the two major reasons. Okay, we're now actually trying to do all these and go back and do more modeling. I think we need to match some of these experimental and theoretical. Then we have confidence on the material response model. So these are the ones that we use convective, only consider convective, and it's like not good. Okay, and the last one I want to show is actually, this is actually John's master thesis. He's finishing up. As a matter of fact, he's going to graduate this semester. This is what we did using modeling for carbon phenolic. Okay, and we have all these 1D using char, and we are matching the surface recession, surface and in-depth temperature, and these we're using a code developed by Adam Emma. He developed this code, and if I'm working with I use NASA code. If I'm working with Air Force, I use Air Force code because they are different. Because I have different customers. I cannot say just use one computer code and I will solve all my problems. No. Now I have a new contract with Navy. Navy have no code that they develop. I'm going to use the Air Force code developed by Air Force. Okay, so we did all these. This is pretty much the input we need to put in order to do 1D, 2D, and 3D. 1D is not really good. We cannot match the experimental data. And now we're moving to 3D. And 3D is not as easy as I thought. I'm putting more people in there to learn, basically solve all these energy equations. See, I'm not in the business of developing computer code. I'm in the business other people's computer code to come up with a materials response model and see whether we could predict some of these performance. Okay, so that's what we're doing. And I think we are the only group that was doing materials measurement and do the model. Okay, so that's why we have a pretty large group that like using Pika, and we are using Dow Corning to shield it, and we come up with a different in situ ablation sensor technique, different from the one that we used before, and we developed that a while ago, 2014, and my student is actually finishing up as a master's thesis. So when I'm done, I'll send a copy to Kathy, and I haven't actually looked at that yet. He said they're going to send it to me on Saturday, so I'm going to mark it up, and then he's going to graduate. So this is his master's thesis about, okay? Testing what I call, go back, the heat flux, time, and that, and compare the average service, total service, and recession, okay? And some of the work that we char, take a look. This is what char predict. This is what we measure. Very, 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 very different. So we need to do more work comparing with char. So that's what we do 3D, because that actually is a 3D problem. You cannot use 1D model to do all that because they are neighboring effect. So now we're going to do 3D. Char is there's another computer code Air Force developed, it's called Hero. You could do 3D because a long time ago our numerical capability is not so good. Everything is do 1D. So now got high power like computers. So everybody's going to go 3D. But even 3D is time consuming. First of all, you need to generate the 3D grid. So it's not as easy as you thought. So this is what we do. It's bad, okay? In like this experimental, it's vertical. Nowhere close to what we expect to see using a 1D model. Okay, so we're moving to 3D. Hopefully, these are the things that he's doing called contact resistant. We're working closely with Johnson because Johnson is the agency who developed this code. They would like us to match some of these things that we do in our lab with the computer code. Okay, so that's what we do, and we talk about all these parameters, and we're doing some sensitivity analysis. Okay, and basically, we're using 1D. We cannot actually do compare with experimental, and there's a lot of problem with the boundary condition because we actually cannot calculate heat transfer coefficient of the acid-acetylene torch. I think I find one of my colleagues who could do that. Okay, we cannot do that. Okay, these are things that we do actually for conclusion and future work. And another way that we start looking at the actually 3D Naval-Stokes CFD this much further down. We would like to have the capability to do some of these analysis in my my group, and we finish all these. Okay, we're doing that in general. Last slide. That we were able to present different things that we do in terms of ablation. Okay, we have been able to make materials for solid rocket. We were able to make material for TPS, and we developed the sensor. Like I said, is from another agency, AFOSR, and we were able to start coming up with what you call material response modeling using Fiat, CMA, and char, and we were able to use OTP and ICP to continue testing this material. I think this is the part that costs a lot of money. Thermophysical product. Okay. The ones that we have is only for PEEP and AFCO and like the carbon phenolic. We would like to use the char strength sensor to give you some information about the char strength. We're going to validate our skill response model using OCP, ICP, and eventually we're going to couple that with CFD. Okay, these are the guys, you see Donald over there, these are the guys that pay me for the last 20 years. And these people actually funded our research in this, not just ablation and all the different things. So that's why I have a dollar sign. But I do actually want to acknowledge people from NASA Johnson, because they have been working very close with us and donate equipment for us to do things. And I need to give acknowledgement to my colleagues that is helping us in terms of ablation modeling. These are all my US citizen students that every year will go to NASA and we will present, they will present, not me, what they have done the past year. Okay? And some of them are going to be NASA employees. And this is my book. And this is, what was the last one? Oh, this is the journal. I'm actually editor-in-chief. With that, I'm going to stop. So this is my book. I'm going to pass on to you and flip it. Okay. This is my expertise in nanocomposites. Okay? And these are flyers in the ancient book. Go buy it. I got 18%. And I use this book to teach actually in ETL. With that, I'm going to stop. Thank you. You go on time.